Okay, so welcome to day 4 of the hottest conference of 2020. Our next speaker is Mitchell Riley from Wesleyan University, and he's going to tell us about synthetic spectra via a monadic and comonadic modality. Go ahead.
Okay, hello everyone, and thank you to the organizers for putting on the hottest conference of the year. I'm very excited to get to talk to, get to share some of the stuff that we've been working on. So this is work that I've been doing with my supervisor, Dan Licata, and also with Eric Finster. So what I'm going to present in this talk is an extension of homotopy type theory, which is going to let us do some stable homotopy type theory in an easier way than reconstructing things like spectra internally. So I'm going to I'll spend the first bit of this talk trying to motivate why we might like such type theory. Ooh. Okay, so going way back to basics, let's just remember that a pointed type is a type and a term of that type, and a pointed function between pointed types is a function between the types together with a path showing that the function preserves the base points of both sides. Now, the path here that's part of the definition of a pointed function is data, which means whenever you do stuff with pointed functions, or you're trying to show that something's a pointed function, you need to carry around the data of these paths through everything. And you often end up having to do all kinds of transports and path algebra, and it can get very complicated very quickly. And what we would really prefer to do is somehow talk about functions between pointed types that preserve the point strictly. But in ordinary homotopy type theory, there's no way for us to specify internally that a function preserves the point strictly. There's no way to talk about judgmental equalities when you're working in the theory. So a very bumped up example of where this kind of data can get troublesome is when we're talking about spectra. So these objects called spectra are the central objects of study in stable homotopy theory, and you can define them internally in more or less the same way as you define them externally. And I'll just say that the reason that people care about these is that these are the things that you use to define homology and cohomology inside homotopy type theory. The definitions you might usually use for normal homology and cohomology don't work internally. So the definitions go via this. So a pre-spectrum is just is a sequence of pointed types, which we're calling these ENs, and a bunch of connecting maps from each type in the sequence to the loop space of the next in the sequence. And then amongst these guys, there are some good ones. So a spectrum is a pre-spectrum where all of these connecting maps are equivalences. So there are some examples of these things which we can define internally. So whenever we have an abelian group, we can define a spectrum where the nth type in the spectrum is the nth Eilenberg-MacLane space for that abelian group. And then one can show that there are equivalences like this that you need. There's also the zero spectrum, where we just take every point in the sequence, every type in the sequence to be the point, and then the connecting maps are just the equivalence between the point and the loop space of the point. And there's also the sphere spectrum, which is easy to describe as a pre-spectrum. So you take the nth type in the sequence to be the n sphere, and then for your connecting map, you can take the transpose of the equivalence between the suspension of the n sphere and the n+1 sphere. So then the transpose of this thing is not an equivalence, but you do get a pre-spectrum. So then maps between these things, if you've got two spectra E and F, then a map between them is a sequence of pointed maps that commute with all of the structure maps of E and F. So if you take the structure map and then the n+1 map, it's the same as taking the nth map and then the structure map. So we need a bunch of appropriate diagrams to commute. And now this is a huge amount of data to specify a map of spectra, because not only do you have all of the pointed maps, which individually have this needing to check that they preserve the point, but then you also have all the data of all of the homotopies showing that the squares commute. So this gets very unwieldy, and not many of the typical operations on spectra, which we might like to do, have been defined in type theory, I think because it gets too complicated too quickly. So something that we could try and do instead is work synthetically. So it's not so much in the spirit of synthetic homotopy theory to basically reconstruct stable homotopy theory internally. So like just reuse all the same definitions. What would be nice if we could use the type theory to do some of the work for us. So one thing we might try is we could try and find a model of type theory where the functions that we define automatically respect the point. And straight away, a problem with that is that pointed spaces or spectra, the categories of these things on their own, don't form a good model of type theory. So that doesn't work exactly. But space-indexed families of pointed spaces or spectra do form a good model of type theory. So this is the semantic situation which we're going to be interested in. So a parameterized pointed space is a space-indexed family of pointed spaces. And the picture we should be thinking about is something like this. So an object, so one of these guys looks like we have some space in the base, and then over every point we have a pointed space, and these things vary continuously as we move around the base. And then if we've got two of these guys, a function between them, a morphism between them is a function of the base spaces, and then corresponding pointed functions of all the fibers. So something which is nice about this setting is that, well, first of all, there's a full subcategory of these guys, which is equivalent to just spaces. So we can take any space that we like as our base space and then just put the point over every point of this base space. So we've got spaces as normal, but then we also have a full subcategory of pointed spaces. So if any pointed space that we like, we can take that as the unique fiber over the point in the base. If we have a type theory which interprets into these things, and we have a function between two of these guys, we know it has, its interpretation in the semantics does preserve the point. So in fact, the infinity category of these guys is a infinity topos, which means we know that it admits a model of type theory with pi's, sigmas, identity types, univalent universes, and a bunch of higher inductive types and all that. So we know we can interpret homotopy type theory as we know it into these objects. We also have the category of parameterized spectra, which is a space indexed family where the objects are space indexed families of spectra. And unfortunately, I don't really know how to draw a different picture of these guys, but it's the same idea. We have just some space in the base, and then over every point we have a spectrum. And then these spectra vary continuously as we move around the base. And just the same, we have all of the, we have a full subcategory of just the spaces and a full subcategory of the spectra. And then Joyal and Biederman in 2008 showed that the infinity category of these guys is an infinity topos, so also admits a model of homotopy type theory. Okay. So when we start learning homotopy type theory, we get used to thinking of types as secretly being infinity groupoids, and then the things like the identity types let us access this extra structure internally. And so when we're thinking of our theory as having a model in these parameterized pointed spaces or parameterized spectra, we're thinking of types as being infinity groupoids indexing a family of pointed things. So I just want to make a quick comparison with the talk from a couple of days ago where Valerie was talking about his index type theory. And he suggested it might be a good theory to talk about spectra. So in his, the way his setup works is that there's an ordinary context. There's a chunk of the theory which is just ordinary homotopy type theory, where everything is would be interpreted as spaces. And then as well as types, there are index types, which are the things which are interpreted as spectra. So in his theory, when you're doing constructions using the ordinary type formers, you're just doing the constructions on spaces. Whereas if we think about our model as being as having all objects interpreted as entire parameterized spectra, instead every object will have both the space information in the base and the information of all the families. So there is sort of a difference in perspective between what I'm about to present and the indexed type theory from a couple of days ago. Okay, so this kind of move where we add stuff to homotopy type theory to sort of expose more structure in our types has been done before. In particular, I'm sure a lot of people have come across this cohesive type theory, or that Mike Schulman wrote a paper on. So in that theory, types are thought of as infinity groupoids equipped with additional topological information, and then there are some more type formers which let you speak about that internally. So I'm going to talk a bit about this as well coming up. Okay, so we know that parameterized pointed spaces or parameterized spectra, we know that they admit a model of HoTT, but there's no way, without adding anything to the theory, there's no way for us to talk about the extra structure which is present in these models. So we should think about what kind of operations we might want to add to the type theory. And so there's a very basic operation, which is if we have one of these parameterized families, we can forget the family and just look at the base space. And in the other direction, we can take any space and equip it with the trivial family, right? So as a diagram of categories, that looks like this. We have our category of parameterized objects and this forgetful functor, which goes down to spaces. And then equipping a space with the trivial family is both a left and a right adjoint to this forgetful operation. So we're gonna, the thing we're gonna try and add to our theory is the round-trip operation, which goes from any pointed family down to the base space and back, giving us the parameterized family with the same base space, but only the trivial pointed thing over in every fiber. Okay, so I'm going to call this a natural. It's a bit of an unfortunate word, but it's just a very bad pun because of the musical notation of spatial type theory. But this operation has a lot of structure. It's an idempotent monad and comonad that is adjoint to itself. So our goal is to come up with an extension of homotopy type theory so that there's a type former which has all of this structure which it does in the intended model. Okay, so that's what the plan is. Perhaps I'll. Are there any questions at this point before I continue? Okay. Okay, so what's coming up is, so first of all, I'm going to talk about Mike's spatial type theory. And I'm trying to explain how you might reconstruct some of the rules of this type theory from scratch. So then with this experience, I'm going to then look at the our type theory, the one with this natural modality. After that, we're going to add some axioms to the theory to try and to hone in on our intended models. And then, unless I've run out of time, I'm going to talk very briefly about what the step after this would be, which is adding a synthetic smash product to the theory. Okay. So let's look at spatial type theory for a bit. Okay, so spatial type theory is a fragment of cohesive type theory, which is the type theory which Mike talks about in his paper. So in cohesive type theory, there are 3 type formers and a bunch of axioms that you might impose. But so spatial type theory is just the fragment which includes the flat and sharp type former. And the intended models of these guys, of this type theory is local toposes. So we have some topos here, and then the global sections functor has both a left and a right adjoint. And the idea is we should be thinking of objects of this category as spaces with structure of some kind. And then the 2 functors on the left and right equip any space with the discrete version of that structure or the co-discrete version of that structure. So the flat type former is when you take the round trip that goes down to spaces and then up discretely. And then the sharp type former is when you go down and then up co-discretely. So we've got flat is a left exact idempotent comonad, sharp is a idempotent monad, flat is adjoint to sharp, and we want a type theory which captures these operations. All right, so how do we do this? So we're going to follow the general pattern of adjoint logic, which is we're going to put in a judgmental version of the left adjoint, flat, and then have the type formers in the theory interact with the judgmental operation. So in general, a term judgment of this theory is going to look like this. So we've split our context into 2 zones. And so this part of the context is just is meant to be an entirely ordinary context. And here, the delta part is going to look like it's going to be the so-called modal zone of the context. So this is also going to consist of variable names and types, but the difference is that a judgment like this is supposed to be interpreted as we think of everything in delta as being as having the flat applied to it. So term judgment like this corresponds to a map from flat delta cross gamma to A. And this is just forgetting about dependence, just to keep things simple. Right. Okay, so first up, what kind of structural rules do we have if we're thinking of this as being interpreted as that? Well, first of all, we have an ordinary variable rule. So if we've got just some assumption, which is in gamma, then we should be able to use it just like we do in ordinary type theory, because gamma is supposed to behave just like an ordinary context. So we've got this rule. But then we also have a rule which lets us use variables from the modal context. And so, I mean, morally, this x here is sort of hidden behind the flat. And what lets us use it is the fact that this flat is supposed to be a comonad. So in particular, we have a co-unit, which lets us extract the A out of this part and gives us a map from this, the interpretation of this context into A. And something to note here, which is a nice part of the theory, is that the raw syntax for using a variable in this way is exactly the same as using it as though it's an ordinary variable. So even though morally these are different judgments, when you're working informally, this kind of move actually does help out a bit. All right. So I'm not really going to care so much about the flat type former. Instead, because it's not going to come up later. But let's just try and figure out what the rules for the sharp type former are supposed to be. All right. So this sharp type former is supposed to be right adjoint to the judgmental flat. So we need to figure out what applying flat to a context does to it. So remember, a context is supposed to be interpreted as this. So if we apply flat to this thing, well, first of all, flat is left exact, so it distributes over the product. Then we've got idempotence, lets us reduce this to just one flat, and then left exactness in the other direction gets us to here. So applying the judgmental version of flat to a general context, what it does is it takes the gamma bit and it moves it over into the special part of the context and leaves the ordinary part of the context empty. Okay, so so how does this help us for sharp? Well, if sharp is going to be right adjoint to this operation, then we can just make that happen. For example, in the intro rule, where so this side here is flat applied to this context. So then transposing across the adjunction, we should get a map from this context into sharp A. And the formation rule just sort of follows the same pattern. Okay, so the elim rule is takes a little bit more thought. So the first thing we might do is we could just take the intro rule and flip it upside down. So certainly we could have a rule like this, where we've got the sharp on the right here, and then we transpose it, and then we get sort of the judgmental flat on the left here. But from a type theory perspective, this rule is not super convenient. So we're going to try and massage it a bit before we set it as our actual rule. So if you imagine trying to use this rule, so imagine you're trying to prove an A using a sharp A, then if you're going to use this rule, you have to look at your special context and then divide it into two pieces, and then send one piece into the special zone and send the other one into the regular zone. But in fact, the rules of the type theory are such that you would never voluntarily choose to move anything into the regular part of the context. So applying this rule going up, you would never choose to demote gamma, because that only makes it more difficult to prove things with when you would inspect the other rules of the type theory. So without loss of generality, we can assume that whenever you apply this rule going up, you would do it with gamma being empty. So let's just delete gamma and have a rule like this. And the second little change we're going to make is things are much nicer if the context in the conclusions of our rules are as general as possible. And we can make the context in the conclusion here fully general just by weakening what we've got here with some arbitrary context gamma. So so here I've used the same name. I've got a gamma here and a gamma here, but these aren't really the same thing. It's just to keep the letters the same. Okay. All right. Okay. So next up is the natural modality. So that any questions about what I've talked about in this bit? All right. Okay. So now let's look at this this natural modality. Okay, so the semantic setting that we're interested in is very similar. So I mean, we also have an adjoint triple. The difference is that the adjoints on the left and the right are the same, meaning that the flat and the sharp end up being the same operation. And if we wanted, we could use spatial type theory to study these settings of parameterized families, because we could add an axiom that just forces those two operations to be the same. So for example, we could assert that for any type A, the co-unit map of flat followed by the unit map of sharp is always an equivalence. But this is a little bit unsatisfying because whenever we're working with a theory, at some point we might want to use the comonadic properties, at some point we might want to use the monadic properties, and we would have to constantly be transporting across this equivalence. So, I mean, it doesn't really save us much effort. So we want a type theory which captures the situation where these two things are equal directly. So there's a difficulty in this setup which isn't present in the spatial type theory one, which is that there's a non-trivial round trip in the structural maps that the operation has. So if you take the unit followed by the co-unit, in general, this is not the identity. So this, if you think about what this map is doing in terms of the parameterized families, so we've got some general parameterized family, and this composite, what it's doing is on the base, it's the identity on the base space of the family. But then in each fiber, so like in each pointed space, it's taking the entire thing and mapping it to the point of that fiber. So that's definitely not the identity in general. So so we need to take this into account. And so in spatial type theory, the co-unit was silent. So remember, we had this special variable rule, which let us use a variable in the modal context via the co-unit. And this made using the type theory convenient. But in this setting, we can't make both the co-unit and the unit, we can't make both of them silent, because we need to remember when we've passed around this round trip. Right. So through experience, just in trying to work with the theory, it turns out to be more convenient to make the co-unit explicit and the unit silent. So I'll show you what this looks like in the rules in a second, just a warning in advance. Okay, so just like in spatial type theory, we're going to
ask a quick question.
Yes.
When you say silent, does that mean you can derive one from the other, or?
Oh, sorry. So what I meant by silent was so this rule here, which lets us use the variable from the special context, isn't recording the fact that we used the co-unit in the term at all. So this term here is, like, as a piece of raw syntax, literally identical to as though we had used a regular variable. Does that make sense?
Kind of. I'll come back later.
Okay. Oh, this might be clear, more clear on the next slide. Okay, so again, we're going to split our context into two zones. And the meaning of a split context like this, again, means that we've got, we're thinking of delta as having natural applied to it when we do anything. So we've got the ordinary variable rule. So, again, gamma is just treated like an ordinary context, so we can use any assumption that we have in it. But now but now things are a little bit different. So here we have what's the equivalent of the special variable rule from spatial type theory. So here we have an assumption which is hidden behind natural, and we are using it via the co-unit. So to get this term out of the bit under natural, we have to use the co-unit. And we're now going to record this fact in the term. So anytime we use an assumption from the special part of the context, we're going to underline the use of it in the term. So the underline here is not part of the variable name. It's an extra marking on the variable. So what I've got written over here, I've also got it underlined just to remind us that whenever we use this guy, we have to use it underlined. Right. But now we have a third variable rule, because whenever we have an ordinary assumption, we should be able to use it via the round trip on natural. So this rule here means it corresponds to the, well, first to the projection to A, but then the map to natural A and then back to A, right? So so both of these rules have a marking on the variable here. So of course, so these two rules are not, we don't want to be able to confuse these, which is why at least one of them needed to have some kind of annotation. So something which is nice about this convention of having the co-unit explicit and not silent is that whenever we're using an assumption via natural A, then it gets a mark on the term. So anytime we see X underline, it means that the thing that we're looking at only varies over the base space of the assumption. It doesn't vary over the spectral information. Okay.
Before you go on,
Yes.
Could you speak to why in bar round trip the type also became purely varying over the base, whereas
Yes.
in bar
Yes, I think that's the next slide. Oh no, so I'm going to come back to that. So yes, I will explain this in a couple of slides. All right.
Can I just ask, why is the variable in the context in var 0 marked?
Okay, so it probably doesn't really need to be. It's just a reminder that whenever we use an assumption from the piece of the context over here, we have to use it marked. It probably doesn't have to be. I mean, so something which is a little bit silly in the way I've got this written is there are three things in this judgment which are reminding us that it's a special variable. So first of all, it's to the left of the bar. Second of all, it's got double colons, and then third of all, it's underlined. So I mean, really, we only needed one of those things, but it's really just sort of hammering it home. Okay. All right. Okay, so let's look at what this operation does on context. So like last time, I mean, the calculation is exactly the same. We've got left exactness distributed over the product, then the double natural becomes a single one, and then left exactness takes us back. So so we want to write something like this, but we can't literally write this because the co-unit isn't silent anymore. So gamma here in general is a list of variable names and types of those variables, and of course everything could depend on the stuff before it. So if we have stuff in gamma which depends on the stuff before it via the normal variable rule, that's no longer valid when we have everything lying to the left of the bar like this. So we have to fiddle with the types of everything in gamma for them to be well formed. So just to remind us, I'm going to write this. I'm just going to write 0 gamma for this. What we have to do is anytime in gamma a variable from gamma is used, it needs to get underlined, right? And the rules of the theory are such that when you do this, everything stays well typed. So just as an example, if we start with a context like this, and we apply this operation, well, then we move everything over to the left of the bar, which means these things become now special variables. But also the type of z here changes. We can no longer write a regular y here because the only way to use y is with a mark. So it has to be marked when we do this move. Okay.
Quick question. Is it obvious that C of y underlined is always valid whenever C of y is?
It's valid when you're doing this move to
Okay.
an entire sort of context telescope like this. You can't switch the markedness or unmarkedness of a variable whenever you like. But in this situation, it does work.
Okay.
I don't know if that's
fine. Thanks.
obvious. Yeah.
So if I could just jump in on that question. So this is sort of a combination of an application of a functor combined with like the left exactness, perhaps?
Yeah, that's the idea. It's sort of, I don't really have a slide for this because I was trying to avoid talking about dependency too much, but this is sort of what has to happen when you sort of distribute the natural all the way down to the variables. And I believe left exactness is what sort of allows natural to commute with context extension, but I'm a bit shaky on that. I don't really remember.
All right, thank you.
Okay, so now I can explain what this piece of notation was. So what we've built into the variable rules is the unit and the co-unit just on those single variables. But one can show that there are admissible structural rules which apply the unit and the co-unit to general terms. So if we have a general judgment like this, we might like to precompose with the unit. And so if we think of the map from this into delta 0 gamma into delta bar gamma, then we should get something in this context. And the way the admissible rule works is we just go through the term and the type here and underline all of the free variables that come from gamma, right? And this is always well typed. And in the other direction, we should also be able to precompose with the unit, and indeed we can. But when you do this, you don't have to change the term at all. So this is literally the same piece of raw syntax is well typed in both of these contexts. So this is sort of what I meant by the co-unit being marked and the unit being silent. Okay. And now I can explain why we had to have that underlying business in the round trip rule. So here we sort of have the base case of using the base case of the round trip. So we're using the variable x via the round trip, but we should also be applying the round trip to the type. So when I write the underline a here, I mean the type A, which has been passed through both of these admissible rules. So what this means is just like underlining all of the free variables in the type A. Right. Okay, so now we've talked a lot about the judgmental structure. Let's talk about the actual type former. So first up, for the intro rule, we have exactly the same thing as we did for sharp. So here we've got natural applied to this context down here, and then transposing it across the adjunction would give us a rule like this. So this is the rule that we want. And again, the elim takes just slightly more thinking. We can take this rule and flip it upside down for the other direction of the adjoint bijection. But again, this context down here is not as general as it could be. So what we're going to do is we're going to build in an instance of this unit rule to our elim rule. So we're going to, rather than applying this rule on its own and ending up with this context which is not fully general, we're going to apply this kind of proto rule and then build in the unit. So in contrast to what we had to do with sharp, where we had to drop this gamma, there wasn't really a good way to use it. Here we can keep gamma, And we end up with this very strange looking rule where the context doesn't change at all between the premise and the conclusion. But this does actually do the right thing, maybe surprisingly. Okay, so all on one slide, these are the rules for natural. So these ones we've already talked about. We have the beta rule, which tells us that for whenever we apply the intro, the elim, we may as well have done nothing. And more interesting is the eta rule, which says that whenever we have a term of natural of a type in any context, that term is equal to the term marked, eliminated from natural, and then put straight back in. So this is kind of critical because it lets us mediate between marked and unmarked terms, at least when we're looking at terms of type natural A. Okay, so with all of this stuff set up, you can show that natural has all of the properties that we want it to. So it's a left exact monadic modality in the sense of the HoTT book, just like sharp is. It's also comonadic, like flat is, and it's also self-adjoint. So the actual statement of self-adjointness that you can prove internally is the one that looks like this, where we have our maps from natural A to B being the same as our maps from A to natural B, at least when we guard the outside of both sides with a natural. So the idea, the reason we need to do this is that, so these things here are internal Hom objects, and they may actually have interesting information in the families over each function. And in general, the information in those families is actually different between the two sides. But when you apply natural and you're just looking at the space of functions, then they are equivalent. Okay. So now basically we're off to the races and we can start trying to build stuff. So we can say that a type is a space if the unit map is an equivalence. So we can just like for any x, we can mark it and then apply the intro. We get a map like this. So we're saying a type is a space if it's equivalent to its underlying space. And a type is a spectrum if its underlying space is contractible. Right. So now, just as an example of like proving something very basic in the theory, the first thing you might want to check is that anytime you've got a type, its underlying space is actually a space in the sense of the previous slide. So we just have to show that the map like this is an equivalence from natural A marked to natural A marked. So for an inverse, we can use the co-unit. So this is just the elim applied to a term of this. And then checking the round trips. In one direction, if we take this and substitute it into here, we've got this term marked and then introed. So then remember, all that marking a term does is it just marks all of the free variables. So this pushes inside and we end up with this. And then the eta rule is exactly, or the uniqueness rule is exactly this equation here. So that's one direction. And then the other direction is slightly more interesting. So if we substitute this into here, we have that marked V, then intro, then elim. The beta rule straight away tells us that this is the same as marked V. But we're not done because that doesn't give us the identity in general. But we can show that it does in this case because we can use the eta rule in the other direction to this one to get this. So we have our term here and we've double underlined it because on the inside we've got the marked variable rule. And on the outside, we've got the admissible marking rule. So then what the admissible marking rule does is it just underlines all of the free variables. So in this case, I mean, the variable's already underlined, so it stays the same. And then we can use the eta rule just in the other direction to get this. Okay, so that's how just something like this is proven using. Okay, I'll pause there for a second. Do we have questions? I see there are lots of things in the chat. Oh, I think Dan is
last argument. Can you use that to unmark any term?
No, you can't, because the reason we could apply the eta rule is because this is a term of natural A, right? We only have this equation available to terms of natural A, right? So it's certainly not the case that every term is equal to the same term zeroed. Okay. All right. Okay, so let's talk about some axioms that we might like. So the spectra, the way I've just defined them, there's nothing in the theory which makes them actually behave like spectra. So in particular, I mean, the theory already has a model in, we think we'll have a model in parameterized pointed spaces, but we want something that forces these things to actually behave like spectra. So here's an option which seems good. So anytime, I'll explain this in a second, anytime we've got two spectra, E and F, the wedge inclusion from E wedge F into E cross F is an equivalence. So by a dull spectrum here, what I mean is we can only apply this axiom to spectra which are completely marked. So we can only apply these to spectra which are in contexts entirely in the, which can be written in contexts which are entirely in the special modal zone. And the reason for this is that when we add an axiom as a term, we need to think carefully about whether the axiom holds in every slice category. And if we don't make this restriction, then it actually wouldn't, because if we're looking at the slice over a general context, which will correspond to an entire parameterized spectrum, then the spectra objects in that slice don't actually form a stable category in general, but they do if the context just consists of a space, right? So this restriction here makes sure that these spectra here only vary over the base space of the context where we expect that axiom to hold. So something you can prove from this axiom is that you have that the spectra form, the dull spectra form a stable category in the sense that a square of these is a push-out square if and only if it's a pullback square. And it also follows quickly from that dull spectra and dull maps between them are infinitely connected. Okay. So there's a second axiom which we might like to impose. And for this, we're going to need to assert the existence of a spectrum. We're going to call it blackboard bold S. We're going to call it the sphere spectrum, which then in the intended model will actually be the sphere spectrum living over the point. Right. But in what follows, we're not actually going to need any special properties of this spectrum. It just shows up in the statement of the axiom I'm about to describe. So the first thing you can do with it is you can use a spectrum to build an adjunction between pointed spaces and synthetic spectra in our sense. And this is not tricky to do. If you have a pointed space and you want to turn it into a spectrum, you can take the smash of that pointed space with the sphere spectrum. So this smash here is just the ordinary smash product of types. So it's just the product quotiented out by the wedge sitting inside. And in the other direction, if we have a spectrum, we can turn it into a space by looking at maps from the sphere spectrum into the spectrum we're interested in. And again, in general, this thing is going to have like interesting stuff happening in the families. So we just force it to be a space.
Are those arbitrary maps or are those pointed maps?
When both things here are spectra, it actually turns out to be the same thing. But I've used pointed maps here sort of for symmetry with the smash product, sort of, or to make it more clear, to make it more plausible that these things are actually adjoint. Okay. So with this, you can define the homotopy groups of the spectrum to be, well, first you turn it into a pointed space, and then you calculate the ordinary homotopy groups of that. Okay. So this adjunction here that I've got factors into a sequence of adjunctions. So here I've got sequential pre-spectra and sequential spectra. And by these, I mean the types of pre-spectra and spectra that I defined way back at the start of the talk. If we restrict the types in the sequence to be spaces. So I can see that I'm running out of time, so I'll just say this very quickly. If you have a pointed space, you can turn it into a sequential pre-spectrum as a sequential spectrum, as a suspension spectrum, and this operation is adjoint to taking the zeroed space. And given a sequential pre-spectrum, you can spectrify it, and this includes into sequential pre-spectra. So the details of this have not actually been done in type theory, but I'm just going to pretend that they have for the purposes of this talk. And then finally, if you have a sequential spectrum, you can turn it into a synthetic spectrum. In our sense, there's an adjoint here, which is defined like this. I won't really talk about it, but we can now state what this normalization axiom will be, which is this adjunction between sequential spectra and our synthetic spectra is an adjoint equivalence. So this is our second proposed axiom, and it's a pretty big hammer, it seems. So you can show pretty quickly from this that the homotopy groups of the sphere spectrum, so the definition of this from a couple of slides ago, is equivalent to the stable homotopy groups of the higher inductive spheres. So this is just sort of playing around with definitions and commuting stuff around. I'll in the interest of getting to the next bit, I'll just not talk about this. Okay. So I've only got a couple of minutes left, and I'll speak very quickly about this, what comes next in this type theory, which is to add in a synthetic smash product. So we also want to be able to talk about the smash product of spectra or pointed spaces synthetically. And we need to think about what this is going to look like when applied to families of pointed things. So the operation we're actually interested in is the external smash product, where if we have two of these parameterized families, then what we do for the base is we take the product of the base, and then in every fiber, we look at the fiber of the fibers of the corresponding points in the original objects, and then smash them together as a fiber of the family over here. And what makes this a bit challenging type theoretically is that this is a monoidal product without any structural rules. There's no weakening or contraction. It's a linear tensor. So the way this is going to work in the extension of the type theory is our contexts are going to become even more structured. using an idea from bunched logics and bunched implication, there are going to be two ways of combining contexts together, both an ordinary Cartesian one and a linear one. So this one will correspond to the ordinary product. This one will correspond to the external smash product of these, the parameterized families. So this is what you might write if everything was simply typed, but that's not what we have here. So certainly we know that we have a dependent kind of ordinary context extension. And if we only had a simple version of the smash product, then we would be combining simple types and dependent types in a way that would get very confusing and difficult to use. So what we'd like is some kind of dependent version of this operation here. So there's a question, when does a dependent external smash product make sense? So a type that we might write like this. And we can define such an operation with certain restrictions. And in fact, what we need is that the second type here only depends on the base type, the base space of the first type. And in the theory we've just presented, we now have a syntactic way to enforce that. We can make sense of a dependent external smash whenever the type B only uses the variable here marked. So figuring out how this modality was supposed to work was critical for understanding how on earth we're going to get a dependent smash to work. Okay, and that's what I've got. Thank you very much.
Okay, thanks very much, Mitchell. So let's all thank the speaker. And remember, we don't unmute our microphones for this because it can cause some problems. So I'm the only one who really gets to clap audibly. All right, so we have time for a few questions.
This might be a terrible question, but have you thought about how you could mix and match this modality with the cohesive modalities, so you could get both cohesion and parameterized spectra at the same time, or is that?
We haven't thought about it at all, I'm afraid. We haven't thought about combining them. Yeah, the first step of that, I suppose, would be figuring out semantically what the interactions between all of those operations is supposed to be. Yeah, I'm not sure.
Next question. I could ask about the smash product. You had to go over that pretty quickly. Is your idea to try to write down axioms or properties that a smash would have, not to construct a smash product, but just to formalize what
that's right.
one would expect, right?
Right. So this wouldn't mean constructing the smash product. It would be further extending the type theory with more rules and more context structure to make it work.
Right. Okay. Because actually constructing it is one of those notoriously hard problems in stable homotopy.
Right. Right. And so hopefully this will let us sidestep that for a bit.
Okay.
Egbert has his hand up, so maybe.
Go ahead, Egbert.
Yes, thank you for the very nice talk. I wanted to ask, in ordinary homotopy type theory, when you define spectra with this additional path as data, what you automatically get is the type of all spectra. And do you lose that in your setting, or do you still have a type of all spectra?
A type of all spectra?
Yeah.
Isn't it just a type of modal objects?
It's maybe I can chime in. It's the type of connected objects for the natural modality.
Oh, right. Yes. Yes. Sorry,
Yeah.
I didn't quite understand. So yeah. Yeah.
Will it be a space in your sense, or
Sorry.
will this be a space in the sense you defined in this talk?
Oh, good question. I guess you have to apply natural to it. No, right.
Yes. So I skipped over this very quickly, but if you were going to write this axiom as a term, what you would really have is you'd have an E and F, which were terms of natural, the type of spectra. So that's what's actually going on here.
Okay. Thank you.
Yeah. So I didn't say it, but so you can add this as a term. You don't need to add this sort of as like a special inference rule.
Incidentally, one more thing I could add is that if you do the naive thing and don't apply natural, there is a canonical parameterized spectra over the space of spectra, which is just over every point, which is a spectrum, that spectrum. So, so it's not at all surprising that the space of spectrum actually gets enriched in this setting, and that you have to apply natural to extract the space.
Is that actually what you get out as the
interestingly, no, which is pretty funny. What you get is what the real answer. So I did lie a little bit. The real answer is that you get the space of spectra, and the fiber over it is one shift, a desuspension of the spectrum, which is funny, but that's what happens. This comes from working out the internal Hom, but yeah, that's what happens. Yeah.
Okay. Time for maybe one more question. Okay, I'll ask one more then. If you do the first bullet point you show and you make a type theory that you can use in practice to do this, is there any chance that something proved here could be automatically translated to a proof in ordinary HoTT about the spectrum objects there?
Mm.
So I guess in a sense I'm asking if in ordinary HoTT you can make a model of this type theory. And maybe the axioms you put, which say that spectra objects should correspond to sequential spectra, could help with that. I'm not sure.
Yeah, so something that you can do is you can define you can define a very weak model of the type theory with natural internally. So you could your type of context really is just the type of a type and a family of pointed types over it, and you can define all of the type formers in terms of that. But then most of the equations you would hope to be judgmental in an ordinary model of type theory are then only propositional. So it's not clear to me how you would sort of, if you had a proof in this strict type theory, how you might kind of elaborate it to a well, yeah, sorry, I'm not sure.
Yeah, okay. That was just a bit out of the blue, that question. All right, I guess it's time.
May I ask a question? Quick.
Sure, go ahead.
So how does cohomology work in the synthetic setting? Do you just map a space into a spectrum using the modal definitions of those? Because it seems like that space component of that, I guess that would give you another spectrum. It seems like naively.
Yeah, so you would want to apply this to the space and then map it into your spectrum. I believe that gives you the right thing. Yeah.
It looks like you might have to apply natural again too. In analogy
yes.
with,
yeah.
At the end, yeah. Okay, because we have another talk and we can use a little break in between, I think it's a good place to stop. So let's thank Mitchell again. All right, and our next talk is Anya Petkovic, who will be speaking at noon Eastern, which is in 25 minutes. See you then.